Hello, everyone. So this is a video lecture it'll be lab 9 for physics 207 and lab 10 for physics 206. And it's going to be on friction. So we're going to study friction in this particular lecture. Okay, so I made the two videos of how I actually collected the data and measured the two types of frictional forces. So you want to make sure you watch those two videos. In the first video, I also described a little bit about friction, but I'm gonna do it a little bit more on the iPad right now. So let me switch over to the iPad and give you a little more background information about friction. Okay, so as I explained in that first video, if you have some object, let me draw this out. Let's say this is like the box of weights that I had in the video, or it could be the cart that we're gonna deal with in lab. And let's assume that it's not moving. So if I exert a force, say in this direction, I pull with some force F in this direction, then since it's not moving, there must be some force that's resisting the motion, and that magnitude of the force is going to be equal to the magnitude with which I'm pulling, right? Think of my force F as like the applied force. So there must be a resisting force that has the same magnitude, so it's the same length, and we call that a static frictional force. So this is F sub S, right? It's a static frictional force. Same magnitude, opposite direction. Why? Because it's not moving, so the acceleration of the object is 0. So if I sum those two forces together, I have to get 0, right? So they have to be opposite direction, same magnitude. Now, you could pull harder. Let's still assume that the object is not moving. So if I pull harder, right, it's still not moving. Therefore, there still is a static frictional force that's resisting the motion, but now it has increased, right, to match exactly the same magnitude that you're pulling with, because the net force would have to be 0. Now, you can keep doing this until the object is on the verge of motion. So you pull even harder, and it's just ready to start moving. So say on verge of motion. So I pull even harder, and it's just ready to start moving, but it isn't moving yet. So this is still a static frictional force that's acting in this direction, right? It would have the same length, same magnitude. But since it's the largest that that static frictional force can be, we call this Fs max. It's the maximal static frictional force. Okay. And then the other situation is if I'm pulling on the object, and let's say it's moving now. So here's my object. Let's say it's moving in this direction, and I want to pull it so that it's moving with a constant velocity. So let's say it has a constant velocity. So I'm pulling right to the left. It's moving with a constant velocity. Now, because it's moving at a constant velocity, that means that there's no acceleration, right? 0 acceleration means the object has constant velocity. Because it has 0 acceleration, that means the net force has to be 0. So again, there must be a force that's resisting the motion, and it must be equal in magnitude to the force that I'm pulling with. So that's another type of frictional force. Now that it's moving, right, this is a little bit different than static friction. We call this kinetic frictional force. So F sub K, the K means kinetic. So Fk is used when the object is moving, and Fs is used when the object is static, when it's not moving. And Fs max in particular is when the object is not moving, but it's right on the verge of motion. If you pulled any harder, it would start moving. Okay, now what's true about Fs and Fk? Well, one thing that's, and you can kind of see from the picture up here, let me bring this back up. right? From these three pictures, you can see that Fs, the static frictional force, is greater than or equal to 0, right? If I'm not pulling at all, there's no static friction. If I pull with a little bit, I have a small static frictional force. If I pull harder, that static frictional force increases. So this can increase. So I'll say it's less than or equal to Fs max. So that's why it's defined there as an inequality, right? It can change. It can go from 0 all the way up to Fs max. Now, there's a nice model for how to compute that maximal static frictional force. So this comes from experiments. It's not exact, but it's a fairly decent model. And what it says is that Fs max is proportional to the normal force. And that proportionality constant we call mu s. And then the normal force I'll just call n. So what is this proportionality constant? This is called the coefficient of static friction. And then the n is the normal force. Let me do a better job with that. And I'll explain normal force in a second. Okay, so Fs max is simply equal to mu s, which is just a number, right? The coefficient of static friction, it's a number that involves the two surfaces that are moving over one another. So in our lab, we had a wooden cart and it had these little leather straps on the bottom and it was sliding along a wooden ramp. So the mu s represents something about those two surfaces, the leather straps and the wooden ramp, that are sliding over one another. Okay, so it should be, in theory, it should be some constant, some number, you know, like 0.9 or 0.7 or whatever it is. It's just some number. And then for the kinetic frictional force, we have a similar formula, right? A similar relationship. And we say that Fk is proportional to the normal force as well, but it has its own proportionality constant, and we call that mu k. So again, what is this mu k? This is the coefficient of kinetic friction. Okay, so what is the normal force? I haven't talked about normal force yet. Well, anytime I have an object that's making contact with the surface, so in this case, right, we have our wooden ramp, which is a flat surface. We had our cart on top of the ramp. And then what are the forces acting on that cart? Well, we have the gravitational force, which is the weight of the cart that's acting down, right? There may be some applied force. Let's say the cart is moving. So I have an applied force to the left, and then I have, let's say it's moving at a constant velocity. I'd have a kinetic frictional force acting to the right. But there's also another force here, right? If the weight were the only vertical force acting, this thing would accelerate downward. And it's not. It's not accelerating in the y direction at all, right? It's staying on the table. So there must be a force that the table exerts on the object in the upward direction. And that's what we call the normal force. So the normal force, let me write the definition of it here. It's the force that the surface exerts on the object and the direction of the normal force is perpendicular to the surface. So the direction of the normal force is perpendicular to the surface. Okay, so in this particular lab, it's pretty straightforward. In fact, the normal force is simply going to be equal to the weight of the object in terms of its magnitude, right? If I look at just the y direction, I have sum of the forces in the y is equal to MAY. But in this case, it's not accelerating the y direction, right? So I have sum of the forces in the y is equal to 0 because the acceleration in the y is 0. And what forces do I have in the y direction? I have the normal force acting up. I have the weight, which is negative mg, acting down. That's got to equal 0. So therefore, the normal force is simply equal to the weight in this case. By the way, these are really, if I'm being careful, these are really all vectors, right? Just drawing magnitudes there, but they're really vectors. Put arrows on top of all these because they're forces. Okay. So in today's lab, the normal force is simply going to be equal to the weight. Now, if you had something more complicated, let me do one, just show you. We're not going to see this in lab today, but you could have something more complicated, right? You could have something, say, on a ramp. So in this case, right, let's say this is my object. What are the forces acting now on the object? Well, you have the weight acting down, right, the gravitational force. Now the normal force, remember, it's perpendicular to the surface. So the normal force would act like this. And then it depends. If the ramp were frictionless, those would be the only two forces. If the ramp had friction and let's say the object was not moving at all, then you'd have a static frictional force acting up the ramp. And if it were on the verge of motion, that static frictional force would actually be Fs max. Okay, so the point I'm getting here is in this case, the normal force is not equal to the weight, right? Because it's at an angle. So you got to be careful. In our case, where it's just sitting on a flat surface, the normal force is simply equal to the weight, right? Very straightforward. Okay, another thing. Which force, Fs max, so the maximal static frictional force, or the kinetic frictional force, do you think is larger? Okay, and here I'll give you sort of a practical example. Let's say you're trying to move a large piece of furniture, right? Like a large couch or something. Is it harder to initiate motion or to keep it moving once you've started? Well, from everyday experience, it's typically harder to initiate the motion, right? It's easier once you have it started moving. And an initiated motion is like when it's on the verge of motion. So that the force that's resisting that is Fs max. And then once you have it moving, the force that's resisting, the frictional force that's resisting motion is the kinetic frictional force, Fk. So therefore, typically Fs max should be larger than Fk. Okay, and that's what you'll see in the video when I have the force versus time graph. You'll always see that the peak, which represents Fs max, is larger than the plateau region, which represents Fk. Now, since the normal force is the same, right, that's just the weight of the cart, that means that μs, the coefficient of static friction, is greater than the coefficient of kinetic friction, right? And in lab today, these are really what we're interested in measuring is μs and μk, those coefficients. They're just numbers that give you information about the two surfaces that are either about to slide over one another or are sliding over one another. Okay, so μs should be larger than μk. And it depends on what the surfaces are. It depends on the individual ramps, the individual leather straps. But typically μs is, anywhere from like 0.6 to 0.8 or 9. And then μk is smaller, anywhere from like 0.3 to 0.5 or something. So US should be larger than UK, but they're just numbers. Okay, let me go to the lab handout. Okay, so here's the lab handout for the frictional force lab. So I already went over this background information, right? Define static friction, kinetic friction. So experiment 1, and really we kind of combine experiment 1 and 2 together, where we're finding the maximal static frictional force and the kinetic frictional force at the same time. So make sure you watch those 2 videos describing how the data was collected, all right? So I give you links here, and I'll put links on Brightspace. And then same thing with the second part. Make sure you watch both of those videos. Okay, so then I filled in part of this table for you. This is the data that I collected, right? Again, you'll see all that when you watch those 2 videos. So we have the 4 conditions. Actually, the first condition was the wooden cart with 2 of those square weights added. Then the second condition is the wooden cart with 3 weights added, then 4 weights added, and 5 weights added. So those are the 4 conditions: the cart with 2 weights, 3 weights, 4 weights, and 5 weights. So I got the mass of the cart by massing it on the scale, and then I converted to kilograms. So this is the mass of the cart. And then, as you'll see in the second video here, using the GLX device, I was able to, from the force versus time graph, figure out what Fs max and Fk, so the maximal static frictional force and the kinetic frictional force, should be for each of those conditions. Okay, and those are the values that I got. It's kind of tricky to get really good data for this particular lab, but did the best we can. All right, so question 1. I want you to calculate the normal force for each of these 4 conditions. Okay, so basically calculate this this third column here, normal force. So how do we find a normal force? Well, remember in this lab, the normal force is simply going to be equal to the weight of the cart. So the normal force is going to be mg. Well, we already have m, right? We have the mass of the cart with the 2 weights and 3 weights and so on. So you just have to multiply that value by 9.8, right, by g, and that's the weight of the cart, and that happens to also be the magnitude of the normal force. So that'll give you the normal force. All right, then question 2 is I'm asking you to calculate the coefficient of static friction and the coefficient of kinetic friction for all 4 conditions. Now, we had the original equations. Remember, Fs max was equal to mu s times n. Well, I can rearrange that equation and I can solve it for mu s, right? If I divide both sides by the normal force, I get mu s is Fs max divided by n. And then same thing for mu k. I take my original equation, which was F sub k, kinetic friction force, is equal to mu k times n, divide both sides by n, and I solve it for mu k. So these are the formulas you want to use to calculate these last 2 columns here. So you're calculating mu s, the coefficient of static friction, and then mu k, the coefficient of kinetic friction. And then you want to average those 2 values. Okay, so once you have the 4 values, just average them. Now, in theory, right, the values should be exactly the same, because remember, these are just constants that depend on those 2 surfaces that are sliding over one another. So in theory, these should be the same, but it's an experiment. They're not going to be exact. So you want to average them, and we're going to call that our representative mu s value, and then average the mu k, so we're going to call that our representative mu k value. And you should find that mu s is larger than mu k. Okay, so, and then show me all your calculations, right? And then make sure you find those averages. Okay, then question 3 and 4, you're gonna do 2 plots. So using Pascal Capstone, you're gonna plot Fs max versus the normal force. So if I look in my table here, the normal force will be your x. So maybe note by making a little x here. Fs max will be your y. So x, y. You want to do a linear fit, right? So we've done a bunch of graphs before, right? A linear fit. And because I'm plotting Fs max as my y variable and the normal force is my x variable, this equation, right, which relates Fs max to normal force is a linear equation. So really you can think of it as y equals mx plus b, right? The linear equation. So you can equate the slope with the coefficient of static friction. So the slope, when you do your linear fit, right? Remember it gives you that slope information. The slope is just going to be your mu s. So you want to record that value, and you record that value in the table right here. That'll be mu s. And hopefully it's pretty close to what you got from your average up here, right? It's just a different way of getting mu s. We're going to get it from the graph instead. And then question 4 is almost identical, except now you're plotting Fk, the kinetic frictional force, versus normal force. So again, normal force will be on the x-axis, and now Fk will be on the y. And then do a linear fit. And then what is that slope equal to? Well, that slope should in theory be equal to mu k. So you're going to record that slope value in here. Okay, and make sure that you include both of those graphs in your lab report. Right, you want to copy and paste them into your lab report. I want to see both those graphs. Okay, there's a few more questions. Question 5 is compare mu s to mu k. Which one is larger? Well, we should find what? Well, we should find mu s is larger than mu k, right? Now compare the frictional forces Fs max and Fk. Which one is larger? Well, if mu s is larger than mu k, what should be true about Fs max compared to Fk? So you want to think about that. If you want, you can think about, you know, your everyday experience, like moving a large piece of furniture. Question 6, describe some advantages and disadvantages of frictional forces in the surrounding environment. So whatever you want to come up with. Disadvantages are kind of easy, right? Because friction can, you know, generate heat. It could seize engines, right? If you don't use oil in your car engine, that's not good. You're going to have problems. Advantages are maybe a little more complicated, but think about like just walking. If the surface of the floor were frictionless, you couldn't even walk, right? So in some sense, friction is an advantage, or yeah, is somewhat of an advantage because it allows you to move. It allows you to walk. It allows you to drive a car, right? If you have a frictionless road, you couldn't even accelerate the car, so you couldn't drive a car. You couldn't take turns. You couldn't even accelerate. So there are some advantages and disadvantages, whatever you guys want to come up with. You want to kind of just research that and come up with a couple of sentences there. And then question 7 is similar. I just want you to come up with a few ways to reduce frictional forces. So obvious ones are like, you know, using lubricants or oil in your car engine. Okay, and then there's one other part. So this is a pretty short lab, but there's one other part. It's a simulation. So you're going to go, actually, it's a similar simulation that you used when you did Newton's second law. So it's the same simulation, forces and motion, basics. So you want to go to that simulation site. And then you want to follow these instructions here, but let me go to the simulation site so I can explain this to you. Okay, so forces and motion, basics. Click on it. Now we're going to click on friction. And what I want you to do is I want you to turn on all these options here. So just put all check marks in there. For the object, you're going to leave just the 50 kilogram crate. That's fine. Okay. And then what we want to do is we want to try and see if we can calculate the coefficient of static friction, so mu s, and the coefficient of kinetic friction, mu k, right, by using the simulation. So we're going to have the guy apply a force, so towards the right. So I'll click this. If you want, you can start around 50. Notice when I apply a force, so let's say right now I have 50, right? I'm applying a force of 50. The object is not moving, therefore there must be a frictional force, right, which is opposing the motion, and it also has the same magnitude of 50 newtons. And what kind of a frictional force is that? It's a static frictional force. If I increase my applied force to 100, then there's 100 newtons that's resisting motion. Now what you should do is increases by 1 newton at a time, right? And of course, the static frictional force keeps increasing as well until the object starts moving, okay? Let's say, this isn't exactly when it's gonna happen, but let's say at 151, right, newtons, the object started moving. Then you know at 150, that was your Fs max, right? You wanna do like one less than when it started moving. So if you figure out the force that gets the object to start moving, if you do one less than that, that must have been your maximal static frictional force, Fs max. And then you can use that value to compute μs, compute the coefficient of static friction, okay? Then once you've done that, then you can increase the force even more. And now, so now I have a net force to the right? It doesn't matter how much you increase it now, because now the kinetic frictional force is going to remain the same. In fact, in this case, it's like 94 newtons. And even when he lets go, now the net force is just a kinetic frictional force, right? There's no applied force anymore. So using that information, this is going to be Fk, you want to compute the coefficient of kinetic friction. You want to compute Uk. Okay, so that should give you enough information to do that. Let me go back to the lab handout for a second. Okay, so again, here are all the instructions, right? But I kind of went over all this already. Started at 100 newtons, increased by 1. And then the maximal static frictional force is going to be 1 Newton less than the applied force needed to get the crate moving. Because as soon as you get it moving, the net frictional force now becomes Fk, which is a lot less than Fs max. So that's why you have to use 1 Newton less than when it started moving, right, for your applied force. That will be the maximal static frictional force. So think about this, right? You have all the information to figure this out. I want you to calculate μs. So that would be the coefficient of static friction between that crate and then the surface, right? And then μk, which is the coefficient of kinetic friction between the crate and that surface. And record the values in the table here. And make sure you show me those two calculations, like how you calculated these two values. And then that would be it for this particular lab report. All right, great. So after this, we just have one more lab report that we're gonna do. It'll be on rotational equilibrium in torques, right? It's a really important concept. So rotational equilibrium in torques. And then after that lab report is done, then there'll be some sort of lab exam. So Physics 207 will have a lab exam on the second half of their course, because since they had a first lab exam. So it'll only cover the last 4 labs, right, that we did online. And then Physics 206 will have a lab exam that involves the entire course, right? Because they just have one lab exam at the end. All right, great.